So, hello everyone. My name is Renan Rocha, and I'm going to present you part of my thesis that's entitled Bayesian Networks, Network Science Applied to Water Resources, Streamflow Analysis and Forecast Incorporating the Non-stationarity. This presentation was supposed to be with my advisor, Francisco de Assis, de Souza Filho. He's a great professor for Federal University of Ceará, but he's facing some health issues and could not be here. So he apologized for his absence. So this presentation is divided in 5 talks. Firstly, I will present to you a little bit of context regarding streamflow simulation, why we need to forecast it, what its importance for Brazil energy systems, and I will tell a little about my objectives of my thesis. My thesis is divided in 4 scientific articles. I'll present only 3 because it's more related to the Bayesian networks, and I already have an extensive presentation, but I'll try to make it short. The first article talks about change point analysis, and it's important to present it because it's based the studies of Bayesian networks. And the other two papers are about it's some Bayesian networks applied to streamflow forecasting, trying to incorporate the influence of the non-stationarity that I detected in the first article. And the last section is the final remarks and conclusions of my thesis. So first of all, Brazil has a national interconnected system of energy production and transmission. In Portuguese, it's called SIM, Sistema Interligado Nacional. And it is a very important system, and it stands out because of this continental scale. Today we have almost 170,000 kilometers, and they expect to be around 200,000 kilometers of transmission lines, just to see about the continual size of this system. And it also has a complex operation. We have a lot of different energy sources, hydropower, thermal, eolic, and nuclear power. And we also have international power exchange with Argentina, Uruguay, and Paraguay. So it's a very big system of energy production and transmission. And in the last decade, there was a considerable increase in renewable energy source. That was the main thing that allowed us as Brazilians to suppress some droughts and to avoid some consequences of these droughts in the hydropower systems, like blackouts and shortages. But still, hydropower is the main energy source, and it plays a key role to provide steady energy production supply, because it can compensate the fluctuations of the renewable energy production. So hydropower, besides its declining trend, it's still the main energy source, and it plays a key role to make a steady energy production for Brazil. So for a single hydropower reservoir operation, it has a lot of factors that may difficult its operation. It has a lot of things that needs to be accounted for when managing operation for hydropower reservoir, like current, water level, water demands, evaporation losses, seasonality, climate variability, energy price, and environmental regulations. So this is some of the factors that we need to account for when operating just for one reservoir. When you look at the scene, we have a lot of reservoirs that interconnected and need to work as a joint strategy to make sure that you don't have problems with energy production. So it's a very complex system that needs a very robust strategy of operation. To develop this robust strategy of operation, we need forecasts of streamflow, because if you don't know how much of water you're going to receive in the hydropower reservoirs, you may find yourself making decisions that will end up with a lot of energy problems. So it strongly relies on streamflow forecasting. But streamflow forecast has its own, it has its own problem. It's very, very, very complexity involved, because it's influenced by large-scale teleconnections patterns with different frequencies, and also you can find non-stationarity in hydrologic time series, like this step change in the streamflow sheets. So this non-stationarity characteristics, it violates the assumptions of diverse classic streamflow forecast methodologies, and thus impose development of new methodologies to detect the existence of change in series and its location, incorporate these characteristics in modeling framework, and evaluate the extension of its consequences. So the objective of my thesis was to develop a methodology to detect change in streamflow series and incorporate these changes using a Bayesian network in streamflow modeling and forecasting framework. The last step about evaluating the extension of this consequence, I used natural science, and they were not present here because I think our presentation is already too lengthy. And why I choose Bayesian networks? Firstly, in the literature, you have a lot of methodologies that want to account for the non-stationarity. But the focus on Bayesian networks is because of recent articles that show these strategies are a promising approach. With recent studies obtain strong results for Streamflow modeling, and also we have this particular characteristic that Bayesian networks and causal networks are being used to predict causality between the values, and it's a very important thing for hydrological studies because mostly we have a very complexity of variables working together to change the patterns of streamflow and precipitation, and it's very hard to account for all the joint patterns together. So we need to first understand more, and that's why people are starting to use causal networks to extract the links, the connections between the variables from the networks obtained from machine learning approaches, and then to get a glimpse of what's really happening and what's the forces behind the streamflow patterns. So the first paper is, as I told you before, is a change point analysis. Change points detection is still an open question in the literature, with recent articles comparing different methodologies and showing that if you use a methodology, you can find a result. If you use another one, maybe find a different result. So nowadays, the problem is how do you test the reliability of the results of a change point analysis? So the first article intended to search for a solution. So, and also the reliability problem of this change point detection problems are amplified when you find yourself using methodologies that are based in cost functions. In the case that I was studying, I used this kind of methodologies. They are highly dependent of choosing penalty value that starts to be very subjective. So that's why we needed to study more about reliability of the results. So the strategy I used was to use synthetic tests to control that with non-change point locations. I think to bring more context about change point location, what we want to do is to find where you have changes in the series, where the step change occurs, and if it occurs. And for the first test, I used a synthetic test with controlled data just to see how this methodology works. And after I used apply the methodology with Brazilian streamflow and climate indices to have these results. So, and also after we detect a change in streamflow series, it's important to see what is the reason behind this change, and if you have like a natural oscillation that explains its occurrence. So I also used causal analysis to verify the relationship between the changes and the patterns in sea surface temperature indices that are very used because they affect streamflow in diverse articles. It's very known in hydrological literature. So talking about a little about the data that we use in this article in this series, we have in Brazil like eight station gauges around 88 streamflow gauges around Brazil. And they come in monthly series, and they are already accounted for anthropogenic derived factors because you have these stations are of hydropower reservoirs. You have a lot of operations, so that's kind of source people remove on the series, so you can have a natural oscillation pattern, not too much affected by my anthropogenic factors. So that way we can connect the variability patterns you see in the streamflow series to climate indices or other sources. So I used these indices. I would just El Niño Sultana oscillation, Pacific decadal oscillation, Atlantic multi-decadal oscillation. These low frequency patterns from that I chose are being used in hydrological studies because they are known to affect the patterns in Brazil and all around the world. And they have a low frequency. So I'm presenting very fast because I think this is just oscillatory to the other results. So for the syntax task, we saw that maybe instead of using a single change point methodology, if you use 3 or more, they converge more when they get the correct change points. So you can use the convergence of the methodologies solution to the reliability problems that we see in change point detections methodologies. And you also found changes in the Streamflow series that I studied in this, that I intended to study in my thesis. And we also saw changes in the climate index that we would expect to. So just show that the methodology is correcting segmenting the series that changes are already known. So the problem with that is that you can see different patterns along Brazil. We have a lot of stations that shows an increasing strength over the latest years, and other side of other stations that saw a decrease from the latest time. So this kind of information is very important for the hydropower system operation, because if you see Streamflow series that have a lower mean for the latest years, you cannot operate it using the mean for the whole series. We will get wrong results. Yeah, and you probably have a model that do not get the forecast right. So that was the main find of this article. We found that you have a lot of step changes along Brazil, and that is motivated. How do we incorporate that in a modeling framework? That's why we tried to get this change and put in a Bayesian framework. And what we saw when you look at this image is that most of these changes can actually be related with the low frequency oscillation of these indices like PDO and AMO. So we have like a connection between the changes in the indices and the changes in the Streamflow. And we find that from this first image that you can see that they are closely up in the years, but also with wavelet coherence analysis that I did not show here, but you can find in the published article if you want to look further into. So it also explains it also makes sense with some literature about how the climate phenomena occurs in Brazil, and the influence of these indices in changes in the South Atlantic convergence zone and meteorological patterns that we are mentioning in literature. So it makes sense that what we saw with the indices and with this methodology are in agreement with the literature. So we have a strong first glimpse that these indices may actually be influencing Streamflow, and maybe a different model for different periods can result in good results, can make good results. So that's how we start the Bayesian approach. And the second article it's entitled Streamflow Forecast through Dynamic Hybrid Gaussian Networks Incorporating the Influence of Low Frequency surface phases. One aspect that I did not tell before is these Bayesian networks are like a data-driven machine learning approach, because we extract the network structure from the data. And so we tried different schemes. This first article, we tried a hybrid Gaussian network as a solution to incorporate the influence of these low frequency indices that I showed you before. So to make sure, just to give a little context, what I call dynamic Bayesian networks, because I input in the network multiple variables for the multiple nodes for the same variables according to the lag desired for the model or to forecast Streamflow. And what I call hybrid is because I put the climate indices as discrete variables in the network, because these networks different from I think the networks that I showed before are continuous, and hybrid because I was in continuous variables are also discrete. So this thesis is investigate different topologies and approaches and to see if it can produce good results in modeling and forecasting Streamflow. So I tried different network topologies, and I analyzed that if I incorporate this influence of low frequency oscillation can produce good results. So I use the same data, but I change a little bit the indices because of how I put the data in the networks, because now I using monthly series, one node for each month, to account for seasonality, because you have strong seasonality in the Streamflow series and hydroclimatic variables. And as I said before, M and PDO were in discrete form. So why I put these nodes in discrete? Because when I put that for network structure learning, if these discrete nodes are used as parents, you will have a different set of parameters if the discrete nodes are considered parents for the Streamflow nodes. So now we'll have a model we'll have a model for each of the phases of the low frequency indices. But the limitation of this approach is that you cannot detect time-limited influences. You will see that change, but you will have the same network structure, and that may be a problem we intended to look into. Okay, and to make sure that I get a model that I can account for its correct modeling approach, I separate with calibration period and simulation period, just to make sure I don't have a overfitted network that will produce good results for a certain period and will produce poor results for the simulation period. And the methodology, I think I jumped it. The methodology that I used to obtain the network was the hydroclimate algorithm, because it minimizes the information criteria. I used Bayesian information criteria as a choice of information criteria to minimize, and it was combined with a bootstrapping procedure to avoid the stop of the algorithm at points of local minimum. And I also put some restrictions to the networks. If you see, I'm putting a lot of variables, so it's very hard to the hydroclimate algorithm to learn a good structure if you don't put restrictions in the network learning algorithm. So some arcs in the networks are illogical for the problem that we are trying to solve it, like Streamflow influence in climate indices that does not make sense in a hydrological point of view. And also the temporality, because you cannot have a temporality violation for the network. So that's or the kind of restriction that you put for the network structure learning algorithm. And I also use the Bayesian learn package in R package that the previous presenter used. So one kind of the particular problem is needed to be analyzed when trying to model Streamflow is because of the normalization problem, because usually they don't follow a Gaussian distribution. So that's something that it's very important for the Gaussian Bayesian networks. And I tried two distinct Streamflow normalization approach to see if it could enhance the results of the networks. And also I tried two different approaches of forecasting. I tried to learn a set of network for each forecast leg that was desirable, and trying to estimate in the Streamflow for long time lags by using a fixed leg 1 network, using Bayesian Inference to estimate for requests with longer lead times. And that's were the two approaches that I investigated in my thesis. So, what I was not expecting is that that was not a significant improvement with the use of a normalization procedure when forecasting directly using the parameters of the network. And I also saw high frequency of negative values for the methods that I used to compare the results. But for each month that I simulated, it improved the results. So maybe normalization it can be a enhancing factor for some stations, because as I pointed for you, these networks were learned for each station of study. So I'm learning like H8 in very big Bayesian networks with a network structuring algorithm. So the structure of the network itself could not be analyzed too deeply in like in-depth analysis, because that was not the point of this article. I was just trying to see if it has modeling and forecasting potential. And what I saw is we have a very spatial pattern. We have some station that's in the SOC region that does not have a good result with this approach, but we have a lot of stations that present very good results for forecasting modeling Streamflow. And what I saw is that we have a lot of variables that are occult in the network. We're trying to forecast Streamflow using only climate indices, but we have a cascade of meteorological phenomena that are occulted, that are between these two variables. And the climate indices, they are of sea surface temperature, they affect the winds, and they affect the precipitation patterns, and the precipitation patterns affect the Streamflow. So we have a gap of the causal sufficiency. Maybe it's not fulfilled. But for some station, they produce a very good results. But for the south part of Brazil, it did not, because this region of Brazil is particularly very affected by precipitation patterns, and the Streamflow characteristics are very different. So if you put the precipitation, the naturals, then you can have a good result. And when we look for the structure itself, as I said, I did not make an in-depth analysis, but I made some classification to see what was happening among them, what variables that they use, the climates usually being used correctly, and you see a very different groups of stations. You can have some stations that are using the same indices, some stations that are not using, some stations very close to each other that produce different results. And this kind of problem is normal when analyzing Streamflow, because maybe some points that are very close, they have a very different hydrologic basins, and they also may be a problem of the network learning problem, network structure learning algorithm that you're using. So that's were the main results for the first parts. When we talk about forecasting, because this first results there that are presented are about simple modeling, but when we look for forecasting, we can see that Bayesian inference allowed us to have better results than having a single network obtained for each forecast leg that we desired. So that's a very particular thing of Bayesian networks that differentiates from the other methodologies that we commonly use for simple forecasting. So I think that's a very, very high gain for the Bayesian networks from this approach. And when you compare the results with the literature, we have some results that are very, very, very good comparing to previous results of previous articles. I will not talk a lot about the numbers, because it's I think it's very specific for hydrologic field, and like this is a multi with different areas. I'm just trying to make a glimpse of everything. So, and what we can observe from this first article, the main message that I want to say to you, that for this approach, Bayesian networks, it can have superior results in comparison with other methodologies like periodic autoregressive models and periodic autoregressive exogenous models. And it can also have the flexibility of using or not the indices. So you can have a methodology that can be more related to a par, or maybe more related to a periodic autoregressive with exogenous variables. So it showed a very good, very potential for the modeling itself, but also a great flexibility to compare with different methodologies. Okay. So that was the first article, and that was the main message I want to say, because this presentation is very long. I'm sorry, I didn't have time to make it short. The second paper is trying a different approach to compensate for the problems that we saw in there, that maybe the use of phase did not produce a good result, and maybe if we try a different structure for different periods of time, we will have better results. So we tried another methodology, network structuring learning, that's called Artiva, and it's presenting interesting potential for this study case, because it seeks simultaneously to detect the change points that delimits the homogeneous periods in network structure, but also it tries to model it. So it solves the two problems in the same time, the change point detection and based on network learning. And it's also compared to the PCMCI. It's a recent methodology that's proposed, and it's used more to infer causality from the network structured learning. So we have two very distinct approaches. One that seeks to detect the change point and provide the network structure with a good modeling framework by all joined together, and the other it's more intended just to infer causality of the network structure learned. And maybe it's again not have the best modeling approach, because you're not trying to maximize the modeling and the forecasting approach of the network. So with using these two different methodologies together, you can compare the performance of Artiva network and PCMC network. So you have a little process, because the data needs to be used in a different way for this kind of methodologies. So we'll not tell a lot about that, just to, as I thought I had more time to present. That was my mistake too. So why PCMCA is used to extract causality from the network learned? Because it aims more reliable networks, and it's combined to a false alarm test like Rochberg measurement. So it's put a lot of, it makes it a lot harder to have weak arcs in the network. So it's getting short of time. We'll be very quickly. Artiva is a change point detection problem. It was not present very good results. It has a lot of promise for the algorithm itself for conversion, and it's hard to evaluate the conversion rates because it has some internal bugs. This R package it's not used anymore because it has some bugs, but it could correctly detect change in 7 stations as the same on the first article. And what we can see from the change in the structure for this methodology, you have different parents according to the different homogeneous periods. So you can see a stronger change in the network structure according to the step changes that we detected. So that's a very interesting result. And what we can see is that the result is not only about the patterns of exogenous variables like climate indices, but you can also see changes in autocorrelation patterns. So that's something that we need to account for future studies. But because of the network structure are very different before the step change and after the step change. And so how you can actually put that in a model without having problems in forecasting. Okay, I have a question here about the manuscript we have available, and this thesis is already presented and published in my university. So I can send you if you want to read it, because here I know it's very, very fast I'm presenting because it's a very lengthy thesis. And what can sort about this problem is because about the results is article can have some change point detection limitations about using a single change point or multiple change points. One thing that I missed saying in the first article is that when we need to use different methodologies for test for reliability, you need to use the convergence of the results. If you use a single change point methodology, you limit the change point detection problem to a single point change point, and that's not be the case. As you can see the figure, in this case, you would have two-step changes for a single period. So that was a limitation for my study. So we jump to the final remarks. The use of multiple change points proved to be a good solution to test the reliability of the results. And the petit test, as I said, since it's a single change point detection, it imposes a limitation to article results. The non-stationarity was incorporated in Streamflow modeling and forecast on two different approaches. And the use of low frequency indices enhanced the results for each station, but did not improve the results for station with change points. So it needs to be further investigated. And it was observed significant change in the network structure, as I said before. And this characteristic needs a more in-depth analysis in future studies. But as I said, Bayesian networks, for this particular case, it showed a great potential and flexibility to model and forecast Streamflow with good forecasting results. But there are particularities that need to be studied for each case, like the forecasting approach, the necessity of normalization, the use of low frequency climate indices phases, and the networks also needs have a wide margin to be improved. The networks were learned here to try to, if the methodology can provide good results. But if you want to use for a single hydropower station to make modeling forecast, you need a further analysis, a more in-depth analysis that was not made in this work because we were trying to see if the methodology had potential for this kind of problem. And clearly it has a great potential to forecast and model Streamflow. Okay, so thank you. I'm sorry the presentation was very fast, but it was very hard to condense my thesis in 30 minutes with people that don't know about the particularities of Brazil. So I try my best. So if anyone wants to have any question, you can send me an email and I'm free to answer it.
Okay. Thank you, Renan. Very interesting topic. And Jeff Weintraub just asked whether manuscripts will be available. I think you answered the question that your thesis, your papers are available. And what I should also point out to everybody, we are collecting all presentations from the presenters and we'll make them available along with the video recordings of the presentations. So you can look at those offline. Do we have any other questions? Just scanning the virtual room. Lionel is raising his hand. Lionel, please.
Yeah. Yes, thanks, Renan, for this presentation. Just two questions. So the first one, you were talking about hybrid network with continuous variable, but perhaps I misunderstood, but I think you were then discretizing them, no?
Yeah, I think it was not clear when I said that. Maybe I reversed the rush. It's hybrid because you have a set of discrete variables that the low frequency indices were used as discrete variables, but the other ones were used as continuous variables.
But did you use them directly as continuous, or did you transform them into discrete?
No, directly as continuous, because if you do not use that for this particular problem, it's very hard to have a good forecast approach.
Okay. And so, and the second one was about, you mentioned that the Bayesian network approach with the dynamic Bayesian network, you had less decay than the other one. I was just curious about when you forecast, how many time steps forward you are predicting. And when you are predicting that, are you using just the output of the Bayesian network, or do you feed the network with some information?
Okay, that point I would need to set more clearly in the presentation. I try to forecast Streamflow for 1 to 8 months with lead time. So I put the networks as the information as evidence and try to infer the Streamflow value. So I tried to forecast within 8 months of like, I don't know if it's clear.
So 8 months, but month by month, or from day 1 to day 1 plus 8 months?
Day 1 to day 1 plus 8 months.
Okay, cool. Thank you.